In today's video, we're going to look at the domain and range of a function. And we're going to look at what these terms mean and how do we find them for different functions. So we spoke about this in the last video where we looked at the domain and the codomain. When you have one of these functions, a function is literally just a mapping from the domain to the codomain. So if you have a list of numbers, they form your domain that then maps using this function, we'll call it f, into our codomain. Okay, so we had one set that is being mapped to another set. The domain of a function, as we said, is just that list of values, but it is the largest set of real numbers for which the function is defined. So let's write that down and then we can talk about it. Okay, so what this means is that if we were to take all real numbers, okay, there may be some set of real numbers for which our function is not defined. So there may be, if we had f of x was our function in function notation, so we have f of x, there may be certain x values, certain real numbers that f cannot map to another set. Okay, there may be some x values for which that function is undefined and therefore that function cannot perform a mapping. We're going to look at some examples of some functions to see what that domain of each function may be. If you are given a table of values, so we looked at this again in our first video, where you are given a table of values, whatever they may be, and then you were given the values that they mapped to. Okay. So in this case, your domain was given. It is just the x value. So if you are given a table of values, those x values that they give you form the domain. When you have a function, so when you are given f of x is equal to something in terms of x, that's where we may need to do some manipulation and figure out what the domain of that function is. What values of x mean that that function is defined so that I can perform a mapping. Okay. So I'm going to do a couple examples here. First one I'm going to do is f of x is equal to x cubed plus 4x plus 6. Okay. If you have any standard polynomial, okay, something that looks like this, whether your leading term is an x squared term, x cubed term like we have here, x to the 6, whatever it might be, anything that looks like this with a standard polynomial has a domain of all real numbers. Couple ways that we can denote that and be aware of this for when you do homeworks and exams, etc. Whenever we say all real numbers, two ways that I want you to write this, or you can write this, is either by doing this R, okay, where we've got a double line at the front, that represents all real numbers, or you can also denote it in set notation, where we have negative infinity to infinity, and you put parentheses around this. We do these rounded parentheses and don't do square brackets. Square brackets around terms in set notation means that you include that term. Because infinity and negative infinity, we don't exactly know what those numbers are. We always put rounded parentheses around it to say that we don't technically include those values because we're just going infinitely on our positive and negative number line. Okay, so all real numbers you can represent either by putting that R or from negative infinity to infinity. They mean the same thing. And that is the case for a domain for any polynomial that would look like this. So anything where you've just got one line of a polynomial where you've got, in this case, we've got x cubed is our leading term. Then you're going to have all real numbers is your domain. Another type of example is where we have a fraction. So this time I've got f of x is equal to 2x over x squared minus 16. If you have a fraction, there are certain values that we cannot have in a denominator. That is, we cannot have a denominator of 0 because you cannot divide by 0 in mathematics. So we have to look at, in this case, we start with all real numbers as our domain, but we have to take some of those values out because this function is not defined when our denominator is 0, because when our denominator is 0, it means we are dividing by 0, which cannot happen. So I have to look at all cases where this denominator term is 0. The way that you find that is by setting it equal to 0. So if I set my denominator equal to 0 and go ahead and solve, you add 16 to both sides, and then you square root both sides, which remember we get a positive and negative value out of that, because both positive 4 and negative 4, if you square them, you get 16. So we know that this denominator x squared minus 16 equals 0 when x equals 4 and when x is equal to negative 4. So our function here is defined for all real numbers except for when x is equal to those two values. So f performs a mapping except for those x values where I know my function is not defined. So my domain is going to be all real numbers, but we're going to take out those two values. So there's a few ways you can write this. You can either do all real numbers and then backslash and then do a set bracket, negative 4 and 4. So that tells me it's all real numbers apart from negative 4 and 4. Another way that you could write this is you could do it in set notation like we did here, but you're going to do the union of sets. What do I mean by that? You start out with negative infinity to infinity, but I do not have a function defined at negative 4 and 4, so I've got to pull those numbers out. So I go from negative infinity to negative 4, not including negative 4. So I take that value out, which means I do rounded parentheses. Union. Then I'm fine between negative 4 and 4. Okay, any value between those, you plug in x is equal to 3. This thing's defined. I don't have a denominator of 0. So I'm fine between those two values, not including those two values. So again, rounded parentheses. Union 4 up to infinity. Okay, so I've taken out the values negative 4 and 4, and it's the union, okay, it's the rest of the set between negative infinity and infinity. So as I said, a couple ways that you could write that. This is probably the simplest way so that you're not having to deal with unions of different sets. Another one that I want to look at is when you deal with square roots. So let's say I've got f of x is equal to the square root of x squared minus 36. This time to find the domain, again, we look at what real numbers is this function defined for? When is it not defined? And wherever it's not defined, you take those values out of your real numbers. So here, with square roots, okay, and in particular with any even root. So this also works for 4th roots, 6th roots, eighth roots, etc. Does not work with odd roots, we'll look at that in a second, but odd roots actually, if you had a cube root or a fifth root, etc., those are actually defined for all real numbers. It doesn't matter. But whenever you have an even root, like a square root, this is where this comes into play. You cannot square root a negative number, or fourth root, or sixth root, or eighth root, a negative number. So we have to make sure that underneath this square root is always 0 and above. Okay, so I know that x squared minus 36 has to be greater than or equal to 0. Okay, it can equal 0 because the square root of 0 is just 0, but it cannot be negative. That's where we get into complex numbers, and we're not dealing with those here. We are just dealing with real numbers. So now we have to think about when this is true. When is x squared greater than or equal to 36? What values of x is this true for? Easiest way to look at this is using a number line. Okay, put 0 in the middle. I'm going to put 6 here and negative 6 here. We know that 6 squared is equal to 36, and we know that negative 6 squared is equal to 36. Question is, what happens between those two values and what happens outside those two values? Well, if x is greater than 6, then x squared is greater than or equal to 36. Okay, so if I took x is equal to 8, x squared is 64. Okay, so I know that everywhere over here that x squared is greater than or equal to 36. Then we'll look at what happens between 0 and 6. What happens in this range? Well, take a value, say 2. X is equal to 2. When x is equal to 2, that's less than 36. So I know that because x squared would in that case equal 4, it's less than 36. Therefore, this inequality is not true. So I know between these two values, between 0 and 6, x squared is less than 36. So that's out. Now let's look between negative 6 and 0. Again, take a value between those two numbers, say negative 2. If I square negative 2, I get 4. 4 again is less than 36, so this inequality is not satisfied. How about over here? Between negative 6 and all the way to negative infinity. What happens between those values? Again, take a value, say x is equal to negative 8. If I square negative 8, I get 64, which again is greater than 36. So I know that between negative infinity and up to negative 6, including negative 6, this inequality is satisfied. Because negative 6 is included and this inequality is true at that point, I include negative 6, so I put square brackets around it. And again, including 6, starting at 6, all the way up to infinity, again, this inequality holds true. So the domain for this particular function is negative infinity up to negative 6, including negative 6, union 6 up to infinity. Okay. Another way that you could write this, again, it's completely up to you. You can say in set notation, it's all values x such that, and such that we represent by a line, x is less than or equal to negative 6, x is greater than or equal to 6. Close set brackets. Okay. In this case, I think it's easier to write it like this, but again, completely up to you, whichever way you're more comfortable with. Either using the interval notation like we did at first, or using set notation like we've done down here. And all that set notation means is it's all x values, all real numbers x, such that x is less than or equal to negative 6, x is greater than or equal to 6. So main things that we really need to watch out for. Number one is fractions. And number two is any kind of even root. Where they really get you is when you have fractions and even roots put together. That's where we really need to be aware of what the domain is. I'm going to go through a couple more examples where we kind of combine some of this stuff just to make sure that we are all on the same page. And then we're going to go through what our definitions are of range and codomain. So the first example that we're going to have is for the function f of x is equal to x plus 7 over x cubed minus 9x. And the question is, what is the domain of this function? Well, we have a fraction here, so we know that we cannot divide by 0. So I need to look at the places where the denominator is 0 and take those out of my real numbers, and that will give me my domain. So first thing we have to do is look at, where does x cubed minus 9x equal 0? Okay, where is that the case? Well, in order to look at this, we need to factor it. Okay, we have this polynomial here, and in order to find the values of x, easiest way is to factor it. So I'm going to take an x out, which will leave me with this. And then x squared minus 9, I need to factor that. Well, it's a quadratic. You can factor quadratics however you like using the quadratic formula, completely up to you how you do it. That would give me x plus 3 and x minus 3. Okay. So what do I get from this? Well, if any one of these terms equals 0, then the whole thing equals 0, which is what I want. So that tells me that if x is 0, or if x plus 3 equals 0, or if x minus 3 equals 0, then this whole denominator is going to be 0. So that's the case when x is equal to 0. Rearrange this and that gives me x is equal to negative 3, and rearrange this one and it gives me x is equal to positive 3. So there's 3 different values, and you can go ahead and plug these back into x cubed minus 9x, and you should find that that equals 0 whenever you use any one of these 3 x values. So set that denominator equal to 0. You may have to factor it, especially if I'm not going to give you anything that's larger than x cubed as your leading term there, but you'll probably have to factor something here with x cubed or x squared. Factor it out and figure out what values will give you that denominator of 0. So that tells me that my domain is all real numbers, not including 0, negative 3, and 3. You can also write that in interval notation, but it's a lot more difficult because we are taking out negative 3, 0, and 3. That's a lot of values to take out to deal with unions of different sets. So I would highly recommend in this case that you actually just write your domain as that. The next example that I'm going to do is something that includes a square root and a fraction. So now I'm going to have f of x is equal to 5 over the square root of x minus 9. So because of this fraction and square root, I have 2 things I've got to deal with here. I need to look at what x values will give me a 0 on the denominator of my fraction. But also I need to look at what x values give me a negative under the square root, because those are 2 things that I cannot have because it gives me an undefined value, and therefore my function does not exist for those x values because the function is undefined. So I need to look at where is the denominator of my fraction equal to 0. And where is the value under my square root less than 0? Where is it a negative, or where if I square root it, I'm going to end up with complex numbers and not real numbers, which I don't want to deal with. Okay. So let's first deal with this one. Let's deal with the first thing. Where is the square root of x minus 9 equal to 0? Okay. Well, that happens when x is equal to 9. Okay, because I need the square root of 0 is 0, and in order to get a 0 under that square root, x will equal 9. So when x equals 9, you get the square root of 9 minus 9, which equals 0. So I know that my function already is not defined when x equals 9. Okay, we already know that. Now I need to look at the next case where it's not defined, which is when that value under the square root is less than 0, where it's negative. So if x minus 9 is less than 0, that tells me, if you rearrange that inequality, that x is less than 9. Okay. So it's not defined when x equals 9, and it's also not defined when x is less than 9. Okay. You can plug in any value for x that's less than 9 here. So let's say 3. 3 minus 9 is negative 6. The square root of negative 6 is going to not be a real number because you can't square root a negative. So you can see that that is the case for any values less than 9. So I know it's not defined when x equals 9, and I also know it's not defined when x is less than 9. Put these two things together, and you get that it is not defined when x is less than or equal to 9. I've just put the two things together. Okay, if it's not defined when it's less than 9, and it's not defined when x equals 9, then it's not defined when x is less than or equal to 9. Okay, so I've put those two things together. So the domain, okay, couple ways that you can write this. Either it's all x values such that x is strictly greater than 9, okay, because less than or equal to 9 is not defined. So the domain is all values of x that are greater than 9, okay? Or you can write it in set notation, which would be 9 up to infinity, but not including either of those values. We do not include 9 because we know it is not defined at 9. So it is only defined when x is greater than 9. So it's between 9 and infinity, not including those values. Couple more that I want to go through. I said this before, but I just want to make sure that we are all on the same page. Okay. If you have any polynomial, okay, so anything that can be written like this, whether it's you've got a squared value as your leading term, so the highest power, if cube value is your leading term, your highest power, whatever it might be, anything that can be written out in this kind of like in one line without any roots or anything. This thing has a domain of all real numbers. Okay, so anything that looks like this, its domain is just all real numbers, or like I said, you can write it as negative infinity up to infinity. The only other thing that I quickly mentioned that I want to go through is anything that looks like an odd root of any value. I could have x plus or minus anything under there, whatever it might be. Whenever you get an odd root, the domain is still all real numbers. Okay. It's only when we have even roots, like where we were dealing with the square root, it's only those even roots that I have to then be aware of negatives underneath that root. If it is a cube root, a fifth root, a seventh root, whatever it might be, the domain is then all real numbers. It doesn't matter what's underneath that cube root or whatever it might be. It is fine to have the domain of all real numbers. That is because we can take the cube root of a negative. For example, if I took the cube root of, let's do -8. Okay, I'll do a couple of different ones here. Cube root of -8 is -2, because if I do -2 times -2 times -2, I get -8. So -2 cubed is -8. 2 cubed is +8. So unlike with the square root case, I only have one value for each one of my cube roots. Okay, it's not like a square root where I have to worry about positive and negative. That doesn't work with cube roots. It just gives you a single value. Okay. The last thing that I want to look at in this video is the definitions for range and codomain, and a quick example of that, and then we'll talk more about those as we get to graphs of specific functions. When we first looked at functions, I said to you that you had this set that we now know is called our domain, and you have another set that is your codomain, and your function f maps from your domain to your codomain. So your function f takes values x from your domain and it maps them into something that's in the codomain. So the codomain is just all possible values that f could map to. Okay. So for example, when we did, let's say x², as this is the example that I'm going to use. Okay. When you've got your function f, it maps from the real numbers, okay, and then it's going to square those real numbers and give you another real number out. Okay, so a function for the most part is going to map for any polynomial from the real numbers to the real numbers. Okay. Now, the range is just a subset of your codomain. It's just a subset of your codomain, and it is actually the list of values that you actually map to. There are values in your codomain, this larger set, that you don't necessarily get mapped to. Okay? For example, if I had, we'll come back to our x² example in a minute. And for my particular function, whatever f might be, I take each value in my domain and I map to something in my codomain. But each value in my domain can only map to one value in my codomain. I may have extra terms in my codomain that don't get mapped to. That's totally fine, especially because in some cases I might end up with a function where multiple things in my domain map to the same thing in my codomain. So I may have some random terms in my codomain that don't get mapped to. The terms that do get mapped to are called the range. But there may be this larger set. The range may not equal the codomain. I may end up with these extra terms in my codomain that don't get mapped to. So they are not in my range of my function because they are not mapped to, but they are within that larger set that we are mapping into. We just don't necessarily get every value in our codomain as a part of our range. Okay. Let's go back to our f of x is equal to x² example. Okay, this is a very good function to look at in terms of range and codomain to show that they are actually different things. We have a polynomial. A polynomial maps from the real numbers into the real numbers. However, when you square values, the lowest value that you can get out, the lowest value that is mapped to, is 0. Okay? You can take any real number, but if you square it, it becomes positive. It becomes greater than or equal to 0. If you map -5 into your codomain of real numbers by squaring it, -5 becomes 25. It's not -25. So I've cut out a bunch of numbers from my codomain, and it turns out that my range is f of x is greater than or equal to 0. It's all values greater than or equal to 0. Even though my domain is all real numbers, positive or negative, my range is only positive numbers greater than or equal to 0. Okay? But my codomain was all real numbers because I'm mapping from the reals to the reals. It just so happens that I end up with this smaller subset of my codomain that actually gets mapped to, and that is my range. Okay. So the codomain is the largest set that you're mapping into. The range is just the subset of that, of terms that actually get mapped to, that have a certain term in your domain that gets mapped to it. Later on in this section, we are actually going to look at graphs of certain functions, and in that we will be looking at specific ranges of those functions, in particular things such as square roots, fractions, etc. We will be looking at what the domain and range of those are, but you can guarantee that for anything that we're going to do, that codomain is all real numbers. Okay, that is the largest set that we are dealing with, and then we will look at the range. What subset of the real numbers do we actually map to for a particular function?